George Andre, and in today's video I'm going to show you something a little bit interesting. So I'm gonna have this function. Let's see. It's okay. So we have, let's say, this function f of x equals to 1 plus x to the L, but here L will be a real number, so not necessarily an integer. And what I'm gonna do is, I'm going to expand it. So here's what I am gonna do. We know that f of x is infinitely derivable, which means that I can do the Taylor expansion of it, and that will be the sum as n goes to 0, from 0 to infinity, of x to the n over n factorial times the nth derivative of f at the point x equals 0. Okay? Okay, now what I'm gonna do is the first derivative of f of x, which is L, because the power goes down, and then we have 1 plus x all to the power of n minus 1, so it's n minus 1, and eventually the derivative of x plus 1, which is equal to 1. And one can say easily that f prime of 0 is equal to L. Okay? Okay. Now let's go to the second derivative of x. And it's gonna be L, because this L is a constant. And now we bring down this L minus 1 and write it as this. And then we say 1 plus x, and then increase the power with 1. And we have this L times L minus 1 times 1 plus x to the L minus 2. Again, we see that at the point x equals 0, this function, the double derivative of our function f, is equal to L times L minus 1. Okay, now let's go to the third derivative. And hopefully this time you will see what we are going to get. Again, the same rule, constants remain the same, L times L minus 1, and now again we bring down the exponent, and we have L minus 2, and then all multiplied by 1 plus x to the power of L minus 3. Yeah, I mean L minus 2 minus 1, which is L minus 3. Again, we take the point in which x is equal to 0, and we have L times L minus 1 times L minus 2 as the value of the third derivative of f at this point. Okay, so far so good. Now, if we were to, let's say, we were to say that L is a natural number, then what would this mean? Then you will have an nth derivative of f, point x. And we will have as a general rule, because here we have this L times 1 plus x to the power of this thing, L minus 1. Here we had 1 plus x to the power of n minus 2. Here we have 1 plus x to the power of n minus 3. So logically, we will have 1 plus x to the power of L minus L. And then the constants, here we had L, Here we have L times L minus 1. Here we had L times L minus 1 times L minus 2. So therefore, logically, here we should have L times L minus 1 times L minus 2 and multiplied all the way to L minus L plus 1. Why? Because here we stopped at L minus 2, here we stopped at L minus 1, here we stopped at L. So therefore, we should logically stop at L minus L plus 1, which is 1. So here we will have f, that's the antiderivative of f 1 plus x to the power of 0, which is 1, and then all this thing which is shortly said L factorial. And it's easy to see because it's a constant function that at the point x equals 0, the function is going to be equal to L factorial. And therefore, since it's a constant function, one can see easily that the L plus nth derivative of f, of our function f, is going to be 0, no matter what nature of value the n is going to take. So far so good. Now, okay, first off, we was gonna write f of x in terms of this relationship, which is the Taylor expansion. Then we're gonna see the following. And I just forgot something. First off, before writing something like that, we need to determine this thing, which is the nth derivative of f at point 0. But it's pretty straightforward to observe something. First off, one can easily calculate that f of the nth derivative of x, but here we take n smaller than L, which is this gonna be 1 plus x to the power of L minus n times L minus 1 times L minus 2 times dot 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 L minus n plus 1. Okay? Now, listen. In order to understand this logically, you have to look at these examples. At the first derivative, we only had L in front. And here we had this exponential, which is L minus 1. And here, at the second derivative, the exponent decreases with 1. And the constant has become L times L minus 1. Here, at the third derivative, we had something like this. We had L multiplied by L minus 1 multiplied by L minus 2. Or in other words, the product of the previous exponents. And here we had L minus 3, which is the previous exponent, decreased by 1. So hence why we have something like that. But this can easily be written as the nth derivative of f of x is being equal to 1 plus x to the power of L minus 10 times L factorial divided by L minus 10 factorial. Okay, just a reminder that n factorial means 1 times 2 times 3 times dot 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 times n. And this is only defined for the natural numbers. For other numbers, we'll have another function, which I'm going to present to you immediately. Okay, and now we'll take this function at the point x equals to 0, and we will have, okay, well, this 1 plus x, since x becomes 0, this thing will become 1, and therefore we will have L factorial over L minus n factorial. Okay? Okay, so far so good. And now we can finally write the function f of x as the sum from n goes to n equals 0 to infinity, but attention please, since we have this relationship, we will not need to go further from the value L. So therefore, we will have only L. Why? Because at the point L plus 1, L plus 2, L plus 3, and so on, the derivative, I mean the n plus first, n plus 1, n plus 2 derivative of f is going to be 0. And not just for the point x equals 0, but for every x. So therefore, we will only say like this. So we will have x to the L, x to the n divided by n factorial times L factorial divided by L minus n factorial, which some of you might know as the binomial coefficient, as the binomial expansion of 1 plus x to an integer. So therefore it will be n sum from n equals 0 to L of x of n, x to the power of n, times n takes L. Okay? But that was for the case in which L was a natural number. Now let's take L as a real number that's not a natural number. That's not a natural one. Okay? Again, we will have to take into account this relationship. Now, let me take, for instance, the first situation in which L is going to be bigger than 0. Therefore, the nth derivative of x, again, this n, I don't care if it's bigger or smaller than L. All I just can tell you is that I know that this n cannot be equal to L. Therefore, you will have 1 plus x to the power of L minus L times L times L minus 1 times L minus 2 times times L minus n plus 1. Okay. Now hear me out. When one looks at this long product, one may think of actually restraining it, just like we did here. But as I said before, this factorial is only defined for natural numbers. And now I'm going to introduce you the big mama gamma function. Okay, now you can think of this function as a generalization of this factorial. And the definition is gamma of x is equal to integral from 0 to infinity of x, gamma of n, integral from 0 to infinity of x to the n minus 1 times e to the minus x dx. Okay, now one can prove that n, gamma of n, is equal to n minus 1 times gamma of n minus 1. And to further prove that this function is a generalization of the factorial, I'm gonna calculate gamma of 1, which is integral from 0 to infinity of e to the minus x dx. That's minus e to the minus x from 0 and from infinity, which is equal to 1. Ta-da! And as you can observe, for n we don't get the natural numbers, we will have something like this. We'll have gamma of n equals to n minus 1 times gamma minus n minus 1. As I said before, this relationship can be proven, and I leave it to the viewer. Time that's equal to, and this is going to be equal to gamma of n minus 1 times n minus 2 times gamma of n minus 2, which can be blah 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 equal to n minus 1 times n minus 2 times dot 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 times 2 times 1 times gamma of 1. But gamma of 1 is 1, and this product is n factorial. So therefore, n minus 1 factorial. So therefore, one can say that for n, a natural number, gamma of n is equal to n minus 1 factorial. Okay, so far so good, but what I meant by this. Okay, take a look at this relationship for a moment. And let's try to apply it here, with this case. What will be, I change it to green. What will be gamma of L plus 1 equal to? It'll be equal to L times gamma of L, which will be further equal to L times L minus 1 times gamma of L minus 1, and so on. So we'll continue with this logic, and finally we will get to this relationship. L times L minus 1 times L minus 2 times dot dot dot, that's L minus n plus 1 gamma of L minus n plus 1. So therefore, the product in question is gonna be L times L minus 1 times L minus 2 times dot 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 times gamma L minus n plus 1 will be equal to gamma of L plus 1 over gamma of L minus n plus 1. Okay, so therefore we have the nth derivative of f the nth derivative of n of x is net equal to 1 plus x to the power of L minus n times gamma of L plus 1 over gamma of L minus n plus 1. So therefore our function can be Taylor expanded as sum from n equals 0 to infinity of x to the n over n factorial. Okay, knowing that as we substitute this x with 0, this function will have the value equal to this ratio. Therefore, we will have gamma of L plus 1 divided by gamma of L minus n plus 1. Okay? So pretty much this resembles very much to our binomial expansion as we knew and as I showed here. Now, what do we do when L is negative? Because spoiler alert, this function gamma is divergent for n being a negative integer. It diverges. Now here's what we can do. We do what we did here, basically. I mean, we write f of n, and the nth derivative of x, of f of x the same as we've written here. Okay, L times n minus 1 times n minus 2 times dot L minus n plus 1. Okay. But here for L integer or not, we can have something like this. Since L is minus its absolute value, we can substitute this here and we'll have 1 plus x to the minus the absolute value of L minus 1 times minus the absolute value L minus the absolute value of L minus 1 minus the absolute value of L minus 2 minus the absolute value of L minus n plus 1. Okay, now let's start counting number of parentheses. This is the first thing. This is the first parenthesis. That's the second parenthesis. That's the third parenthesis. So therefore, here it's subset 2 is the third parenthesis. So logically, this must be the nth parenthesis, right? So, if we are to extract all of the minuses from these parentheses, we will have something like this. Minus 1 to the n times 1 plus x to the power of minus the absolute value of L minus n and multiplied by the absolute value of L times the absolute value of L plus 1, because we extracted the minus from each parenthesis, times the absolute value of L plus 2, every minus, and all the way times the absolute value of L plus n plus 1. Okay, now let's take a look at this nasty product here. Isn't it that this does resemble this? Well, that's correct. It resembles, except from the fact that instead of minuses here, here, and here, we have only pluses. But there's no problem. There's no problem with that, because one can say that the absolute value of L plus N plus 2, as we can derive from this recursive relationship, is divided by the gamma of the absolute value of L is equal to this nasty product, which is L times absolute value of L times the absolute value of L plus 1 times the absolute value of L plus 2 times dot 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 times the absolute value of L plus N plus 1. Okay. Now, we want to see what happens when x equals 0 for this function. And we will have the nth derivative of f at the point x equals 0 is equal to minus 1 to the n times this product, which can be written like this. So, gamma of the absolute value of L plus N plus 2 divided by gamma of L absolute value of L. Therefore, our function f of x can be written as the sum from n goes to 0, n equals 0 to infinity of 1 minus x to the n, minus x to the n, because we have minus 1 to the n, and I multiplied here with x to the n, and which gives me this. Now this is over 1, n factorial, and then all multiplied by this ratio, which is gamma of the absolute value of n plus L plus 2 divided by gamma of the absolute value of L. Okay, hopefully you understood what happened here. So I want to exercise a little bit just to show what happens a little bit. Let me exercise size let's have this function f of x is equal to square root of 1 plus x, just for fun. Okay, exercise. So according to what we've done here, this function can be Taylor expanded as a sum from n equals 0 to infinity of x to the n over n factorial times, here our L will be 1/2, so we'll have gamma of 3/2 divided by gamma of 3/2 minus n plus minus n, sorry. Now, spoiler alert. So let's calculate this gamma. Here we have integral from 0 to infinity of x to the 1/2 according to our definition, yes, x to the 1/2 times e to the x, e to the minus x plus dx. And if we do the u substitution, x to the 1/2 is, which means that x is equal, will be equal to u squared, which means that dx is equal to 2u du. So our gamma of 3/2 is gonna be equal to 2 times u squared e to the minus u squared du, but that is going to resemble something. I mean, it's going to be similar to something that we've studied in some other videos of mine. I'm just gonna show you immediately. So we have, okay, here I'm going to do integration, a little bit of integration by parts. I mean, the same technique that can be used to prove these things, this relationship. And I'm gonna have u minus e to the minus u squared from 0 to infinity. That's gonna be 0 minus integral from 0 to infinity. Sorry, I thought this, I think this is minus here, and plus there. And we're gonna have minus u squared du. Minus u squared du. But actually, I think we've calculated this integral at the live from Facebook, and the result was square root of pi over 2, if I'm not mistaken. Okay, so basically our gamma of 3/2 is going to be square root of pi over 2. Which means that according to our recursive relationship, we will have gamma of 1/2 is going to be 3/2, gamma of 3/2 over 1/2. That's going to be square root of pi, which is an interesting result that you need to keep in mind for this exercise, for the sake of this exercise. Why? I'm just gonna show you immediately. So 3/2 minus 2, gamma of 3/2 minus 2 is gonna be gamma of minus 1/2, which is gonna be gamma of 1/2 over minus 1/2, which is gonna be minus 2 square root of pi. And gamma of 3/2 minus 3, it's gonna be gamma of minus 3/2, which is gonna be gamma of minus a half over minus 3/2, but that's gonna be 4 over 3 gamma, 4 over 3 square root of pi. And gamma of 3/2 minus 4, that's going to be equal to minus gamma of minus 5/2, which is equal to gamma of minus 3/2 over over minus 5/2, which is going to be minus 2/5 times this result, and that's gonna be minus 8 over 15 square root of pi, and so on. I'm not gonna calculate the rest of the terms, but I think you've got the idea. But this is a way we can expand this relationship. But before I end this video, I'd like to give you a little bit of a shout out. I mean, not really a shout out, a little bit of a thing. Let's say we will have the function square root of 1 plus x squared. What we can do to expand it? Well, first off, we took as example this function. So one can say it's f times x squared. It's f of x squared, sorry, which replaced into this relationship can be written as and the sum from n equals 0 to infinity of x to the 2n divided by n factorial times gamma of 3 halves over gamma of 3 halves minus n. Okay, so that's the end of this video. If you like it, don't forget to give me a like, follow and share. And see you next time. Goodbye.